All right. Now, just like in confidence intervals, there was a 4-step process we had to go through. We had to define the parameter, explain what the problem was about. Then we had to say, were we allowed to do it? Check conditions. And then we had to do the work, and then we had to interpret it in context. Well, for a significance test, it's the same thing, a 4-step process. And the 4-step process, luckily for us, is exactly the same. What are we going to do? Are we allowed to do it? Do it. Tell us what it means. Same as in a confidence interval, 4 steps. And the conditions are what we're going to look at right now. The conditions of a significance test are the same as they were for a confidence interval. Now, here we're going to look at the conditions for a categorical problem or conditions for P. If it's a proportion, what are the conditions? Well, SRS has to be from a simple random sample. How do we know? They tell us. Then independence. The population must be 10 times the size of the sample. And that's what this 10% condition here is saying. N must be less than 0.1 times capital N, where little n is the sample and big N is the population. I like it better in this. The population must be 10 times the size of the sample. And then it has to be normal. How do we check for normality for a proportion? Well, same as before, N times P naught. Why are they putting P naught? They're saying that N times the null proportion and N times the proportion 1 minus the null proportion, both must be greater than or equal to 10 for normality. So to check the conditions, we have to make sure that it's random, independent, and normal. So, and this is the process for doing this: SRS, independence, and normality. Okay. All right. So previously in significance testing thus far, all the work has been done for us. They've told us what the p-value is, but it's just been magically placed in the examples. We haven't seen where does a p-value come from. We know what it is. It's the probability of finding a result as extreme or more extreme than the result that we found, assuming the null hypothesis is true. But how do we calculate it? Where does it come from? And that's what we're going to look at now. In order to find a p-value, first we need to find the test statistic. Okay. So the test statistic is going to lead us to table A or table B, which will then lead us to a p-value, which in turn will give us our conclusion. Okay. So where do we get this test statistic from? Well, right now we're going to have 2 types of test statistics. We're either going to have a z-test statistic or a t-test statistic. Okay? And if it's a proportion question, it's always going to be z. Z likes P like Z, pizza, P like Z, always. If it's a proportion, we use Z. Okay? So the standardized test statistic measures how far a sample statistic is from what we would expect if the null were true. Remember, all a z-score is, or a standardized test statistic, is the number of standard deviations away from the mean. Okay? So they write it out here for us. The standardized test statistic equals the statistic minus the parameter divided by the standard deviation of the statistic. So we'll look at the specific test statistics. There's a different one depending on whether we're doing categorical or quantitative data. This example that we're going to look at right now is going to look at proportions. An administrator at a local high school decided to perform the test that the proportion of students who eat, or the proportion of students who have a part-time job is less than 25%. So you can see the null and alternative right here. What is P? The true proportion of students at this school that have a part-time job. Always define the parameter and context of the problem. What are we doing here? What is this problem about? Well, P, this problem is or what we're going to test is the true proportion of students at this school that have a part-time job. Okay. Now, let's assume that all the conditions have been met. Let's assume that it's an SRS. Let's assume that it's independent, and let's assume that it's normal. Okay, and I think you could see that it would be, assuming there was more than 2,000 students at the school. 0.25 times 200 would be 50. 1 minus 0.25 times 200 would be 150, both greater than or equal to 10. And they tell us that these students were randomly selected from our school. Okay. Explain why the sample results gives some evidence for the alternative hypothesis. Okay. Well, what were the sample results? The administrator randomly selected 200 students and found that 39 of them have a part-time job. So P hat, the sample proportion, is 39 over 200, or 0.195. So P hat is 19.5%. We're testing the alternative of P, or the null of P equals 0.25 versus the alternative that P is less than 0.25. So we suspect that less than 25% of our students are actually working. Well, is this 19.5% uncommon? Is it statistically significant? Is it far enough away from the hypothesized value for us to not believe that 0.25 is true? Or is it likely just due to sampling variability or chance alone? So part A, explain why the sample result gives some evidence for the alternative. So why does this somehow give us a little bit of evidence that maybe it's less than 25%? Well, it's less than 0.25. It's 0.195. So we have some evidence that it's not equal to 0.25. But is that far enough away? Is that data statistically significant for us to conclude that truly less than 25%? Or is this 0.195 relatively common if the true answer was 0.25? So due to sampling variability, is this relatively common or not? Explain why the sample results give us some evidence. Well, it's less than 0.25. Calculate the standardized test statistic and the p-value. All right, so I've been talking to you about this through this whole unit so far. We're going to look at how we calculate the p-value. So for the sample proportion for a one sample Z test, how are we going to do this? Well, Z equals the standardized test statistic equals the statistic. In this case, the statistic is P hat minus the parameter, which is P naught from the null, over the standard deviation of P naught. So that would be P naught times 1 minus P naught all over N. So I have all this data. Now I'm just going to plug and chug. Okay, so P hat is 0.195 minus the proportion from the known alternative, or minus 0.25 divided by the square root of 0.25 times 1 minus 0.25 over n. In this case, n was 200. We randomly selected 200 students. Okay, I'm not going to show you how to plug all those numbers into the calculator and push buttons because I'm pretty sure that you guys would be able to do that on your own. So our Z test statistic, our standardized test statistic is negative 1.8. So assuming that 0.25 is the true answer, finding a sample of 0.195 or smaller out of a sample of size 200 would be 1.8 standard deviations below the mean. Well, how does that then help me find the p-value? Well, first let's look at our favorite table, table A. So assuming the null is true, that the mean is 0.25, what's the probability of getting a sample of 0.195 or smaller? So if we grab table A and look it up, this is where we're going to find this magical p-value. Okay, remember Z was negative 1.8. So I'm going to come to the table and I'm going to look up negative 1.8. Oh, 0.0359. That is our p-value. It's the same as calculating the z-score. Why am I looking at less than? Well, because the alternative was less than. Since the alternative here is less than, then on the table, I'm going to simply use what I find. Because remember, the table can only give us less than. So a z-score of negative 1.8, a value of 0.195 or smaller, assuming that 0.25 is the true population's parameter, would happen 0.0359. That is our p-value. Our p-value is equal to 0.0359. So this is part B. Calculate the test statistic and find the p-value. Well, you know what? The calculator can also find the test statistic and the p-value for us. Let's take a look at our favorite tool here, the TI, and let's see how we would conduct this. What are we going to do here? We're going to run a test. Okay, remember our favorite button? Stat. What are we going to do? Test. What kind of test is it? Oh, it's a proportion. Do we have one or two proportions? Just one. Okay, so the calculator is going to call this a 1 prop Z test. 1 prop Z test. And it's going to ask us for something. Oh, what's the null? Oh, well, we claim that it's 0.25. That's the proportion of all high school students that have a part-time job. What was X? So how many did we find in our sample that had a part-time job? Oh, 39. Out of how many did we ask? Oh yeah, 200 was our sample size. And then what are we trying to test? Less than, greater than? We think that it's going to be, our school is going to be less than the national average. So we select the less than for the alternative, and then we come down here and we tell it to calculate. And look, it gives us a z-score of negative 1.796. Yeah, we found negative 1.8. It gives us a p-value of 0.0362. We found a p-value of 0.035. Either of these methods is sufficient and will get you 100% credit on the test. If you use technology, the TI, to do this, or if you use z-scores in table A to find the p-value, either of those methods will work just fine. So that's how we would use the calculator to find the p-value and the test statistic. The calculator does all the heavy lifting for us, as you can see. All right, and then finally, part C says, what conclusion would you draw? Okay. Well, the p-value we calculated was 0.0359 or whatever it was, something like that, right around there. But the alpha level is 0.05. Since this p-value is less than the alpha level, we would say that the data is statistically significant. We reject the null and conclude that fewer than 25% of the students at our school have part-time jobs. All right. So we pretty much went through the whole process here. The only thing we left out was checking our conditions. Okay. But remember, they're the same as they were before. And we'll do another example here soon where we look at checking the conditions. Okay. So as a recap of this, there's a 4-step process. What are we going to do? Are we allowed to do it? Do it. What the heck does it mean? Always the same 4-step process. Now, here is a nice little visual of a one sample z-test for a proportion. Suppose that the conditions have been met. The null p equals p naught. The standardized test statistic, or our test statistic, in this case, I'm going to call it our z-test statistic, is the same formula we wrote previously. P hat minus p naught over the square root of p naught times 1 minus p naught divided by n. If the alternative is greater than, then we have to find the area on the right. Well, we know how to do that. We look it up in the table and we subtract from 1. If the alternative is less than, then we just use what we find in the table. And if the alternative is two-sided or not equal to, then we must find the area in both of these two tails. Since this curve is completely symmetrical, if we find the area in one tail, we can just multiply that by 2 to find the area of both tails. So this is how we would construct a one sample z-test. Check our 4 conditions. Find your test statistic, find your p-value, come to your conclusion. So again, real quick before we move on, what are we going to do in context? Are we allowed to do it? Check conditions. Do it. Test statistic, p-value. What the heck does it mean in context? That same 4-step process will be true for any type of significance test. Okay, we've only looked at one right now, one sample z tests. Okay. But let's take a look at some other ones.